Hello everyone, myself Amit Kumar Shukla and today I am here to teach you crystal field splitting or crystal field theory. So the first thing that came into picture is that why there is a need for crystal field theory when we already have a valence bond theory. So it is because valence bond theory have several limitations. For example, it is based upon magnetic moment and it is not able to explain the magnetic moment of change in magnetic moment of some of the complexes. So it was found that there is a need for some other theory that can explain complexes in some better way. So there comes the crystal field theory. So the main postulates that of this crystal field theory are that it says that the interaction between the metal and the ligand is purely ionic. The metal behaves as a positive point charge while the ligand behaves as a negative point charge. Also, if the ligand is neutral, then it will act as a negative dipole kind of charge. Also, it suggests that the force of attraction between this metal and the ligand is purely electrostatic. This metal ligand interaction is electrostatic interaction rather than not a coordinate interaction that was suggested by the valence bond theory. Now, the second thing which this theory proposes is that there are three types of interactions between this metal and ligand. For example, metal and ligand have attractive forces. Attractive interaction. This is the first kind of interaction. Then there can be a repulsion between ligand and ligand electron cloud. The electron clouds of both of ligands can repel each other. Repulsion between ligand electron cloud. Then a third interaction is the repulsion between metal electron cloud and ligand electron cloud. So these are the three types of interaction that are present between the metal and the ligand. Now, moving ahead. One thing that also you need to know to proceed in this theory is that the d orbitals can be subdivided into two types, that are d axial orbitals and non-axial orbitals. So what do you mean by this axial and non-axial orbital? So you know that d orbitals are dxy, dyz, dzx, dx square minus y square and dz square. So the orbitals have shape. I will draw first the shape of orbitals. Like it is x axis and it is y axis, then it is dxy. Second, if it is y-axis, it is z-axis, then it is dyz. Third, if it is z and it is x, then it is zx. Now what you can see is that these orbitals are not, the lobe of these orbitals is not aligned towards the axis, it is in between two axes. Hence these orbitals, these three orbitals are non-axial orbitals. So do you understand why it is non-axial? It is because the orbitals are present in between these axes, not along the axis. That is why the xy, the yz and the zx are known as non-axial orbitals. So the next question is, what are the axial orbitals? So let's see that also. See, if this is x-axis, this is y, then the shape of the x square minus y square is something like this. And if it is a z-axis, and this is this z square. So what you can see clearly here, that the orbitals here are along the axis, along the x-axis and along the y-axis. So this orbital dx square minus y square is an axial orbital. Similarly, the dz square orbital is along the z-axis, hence it is also an axial orbital. So these are the classification of d orbitals. Now moving further in our theory, let's take 5 degenerate d orbitals. See, 1, 2, 3, 4. Wait, I think. Let us consider any metal, d block metal, Mn plus, and it's 5 d orbitals. Now, let us begin with one by one the interaction that are present. For example, there is an attractive interaction between the ligand and the metal, because the metal is positively charged and the ligand is negatively charged. And whenever there is an attractive force, it leads to further stabilization. So these orbitals will get stabilized because of the attractive interaction between the metal and the ligand. So stabilizing means that there will be a decrease in energy, and whenever there is destabilizing, it means there is an increase in energy. So see, so these are my d5 orbitals that are being stabilized because of attraction forces between metal and the ligand. Now let us consider the other interaction, and what is that? That is repulsion between the ligands. Let us see this, it destabilizes further to some extent. Since it is a repulsive interaction, so it will destabilize my d5 orbital. Now focus here, because an important thing is coming. And what is that? That is the repulsion between the metal electron cloud and the ligand electron cloud. That will further destabilize our d orbital. So what we will think that the final picture should be like this, but there is a catch. And what is that? We have just seen that the orbitals are axial and non-axial, and since octahedral geometry looks like this, see, this is an octahedral geometry, and we can see that the ligands are coming from these directions, from this direction, from this direction, and from this direction respectively. So what we can see, that all the incoming ligands will not feel the same level of repulsion when they approaches the metal. In octahedral complexes, the ligand comes along the axis. That is, if it is x, y, z axis, x, y and z axis, then the ligand will approach to the metal center along these x, y and z axis. Then what will happen that the orbitals that were along the axis will face greater repulsion in comparison to the orbitals that are non-axial. So what will happen is that these 5 orbitals will lose their degeneracy and they will become degenerate. So we have to write it like C. So what will be these 3 orbitals and what will be these 2 orbitals? Since we have seen that dxy, dyz and dzx, these 3 are non-axial, so they will face lesser repulsion, hence they will be stabilized, whereas the dx square minus y square and dz square are along the axis, so they will feel greater repulsion from the incoming ligand and they will get destabilized and their energy gets increased. The line that divides this splitting is known as the barycenter. Also, the total energy of splitting, this is total energy gap of splitting, is known as delta naught, that is, and this delta naught is crystal field, should adjust it somewhere, this delta naught is cfse, या crystal field splitting energy. So this is crystal field splitting energy. Now this energy is further minus 2 by 5 delta naught, and this energy is minus 3 by 5 delta naught. Sometimes students get confused because these values are very similar when we study about the tetrahedral splitting and this octahedral splitting. So what you can cross check, how you can cross check that you are writing the energy in the correct order is that you can fill 6 electrons in these 3 orbitals combined. So when you multiply this 6 by this 2, you will get 12 by 5 delta naught. And here you can fill 4 electrons. So when you multiply this 4 into 3 by 5, you will get, this is plus 3 by 5. Then you will get 12 by 5. So both will come 12 by 5. So when you will do same thing for the tetrahedral splitting, then also you will get 12 by 5 for both the cases. So in that way you can memorize it that which one is 2 by 5 and which one is 3 by 5 delta naught. Okay. So moving on to the tetrahedral splitting. I think my point is clear about the octahedral splitting that I have told you. Nitya bhai kafi. So these two separated these splitting orbitals, these lower 3 orbitals have a specific name, and also these upper 2 orbitals have a specific name. And what is that? These orbitals are known as T2G, and these upper orbitals are known as EG. So the first question that comes into my mind of anyone, that what is this T2G and EG? So this T2 and E comes from the molecular energy diagram of the complexes, and this G subscript shows that the geometry is centrosymmetric, that means it is Jared. What it means when you say it is Jared is that, see, if this is a octahedral complex, if this is an octahedral compound, then if you move towards your up, you will find a ligand L. If you move towards down, you will also find a ligand L. For example, if it is for some Ml6 ligand, Ml6 complex, it is for some Ml6 complex, then you will find another ligand L also. If you move in this direction, you will find a ligand L, and if you move in this direction, you will again find an L. So what it means that from the center point, the symmetry in this orbital is same. That is, from center point you will encounter same ligand whether you go on any side of this complex. So this type of geometry is centrosymmetric, and hence here is this G subscript that is coming with T2 and Eg levels. So if I am clear about this octahedral cfse, so the key points that you can take away from this is that the CFT is telling you that the metal and ligand are point charges, metal are positive charges and ligands are negative charges. Okay. The second thing is there is three types of interaction present between the metal and ligand. First one, attraction force between metal and ligand, and that will stabilize the complex. Then second is the repulsive forces between electron cloud of ligands, that will destabilize the complex. And the third one is the repulsion between the metal electron cloud and the ligand electron cloud, and that will further destabilize. Now orbitals are of three types, two types, axial orbitals and non-axial orbitals. So in octahedral geometry, when ligand approaches, then it is approaching towards the axis. So the axial orbital will feel greater repulsion and hence get destabilized, and the non-axial orbitals will get stabilized. The splitting will give rise to two levels. One is T2G level and the other is Eg level. The energy from barycenter to T2G level is minus 2/5 delta naught, and from barycenter to Eg level is plus 3/5 delta naught. This is all about the crystal field splitting of octahedral complex.